hopefully you have a little extra space under example 3 to carry some notes over for example 4, because example 4 is going to take a little bit more room than the other ones did. Now when we look at this, we have a 4th degree polynomial, which means it could have up to 4 x-intercepts, and if you look very closely you'll see that this actually crosses and kind of this little piece right here is above the x-axis, so there actually are 4 zeros here. And I'm just going to kind of put a really light dot here at each of these. The only one that looks like it's exactly on one of the tick marks is this one. It looks like it's on -2. Other than that, it's kind of hard to tell. So let's check -2 to see if it is an x-intercept. And if you're thinking, how would that's so hard to see, if I give you one on this test, I will make it very obvious where the actual zeros are on the graph. So let's put -2 in here, and let's put 4, 6, -12, -19, -6. Now, I could substitute -2 in for x and then just see if this equals 0, but it's actually a lot easier to do this using synthetic division. So if I bring down the first number, which is 4, so notice this number is not always 1, it's always whatever the first coefficient is. -2 times 4 is -8, so this would be -2, and then -2 times -2 is 4, so this is -8. -2 times -8 is +16, so this is -3. -2 times -3 is +6, so this is 0. So we do have a 0 here of this function. But that's only 1. If I divide this is still a cubic graph. And so I have to know something else. So we have these other 3. You can't really read what they are on the graph. These are in between 0 and -1, and this one is in between 1 and 2. So this is where the rational root theorem comes in handy. So I want to go over to the next page, and this, I'm not going to read through this with you, but basically this tells you how to find the zeros of a polynomial. Method 1 is just by factoring, which is what we did with example 3. Method 2 was listing the possible rational zeros using the rational root theorem, and test possible rational zeros to see if any of them are zeros by looking at the graph. So you could actually look at the graph first and then test and then try the rational root theorem, and then kind of going through synthetic division, quadratic formula, etc. Method 3 is not something we're actually going to be doing, but there are times when you can't find any zeros, and the only way you can do it is to look on use technology to estimate them. So that's what that method 3 is saying. There is a video about the rational root theorem, but I just wanted to show you basic, and that goes into it in a little more detail. But the rational root theorem just says that in order to find the only possible rational numbers like that can be written in fraction or whole number form, that are zeros of the polynomial, are factors of the constant divided by factors of the leading coefficient. So I give you an example here. The reason that has to be true is that when I multiply out these factors, they have to give that last number has to be the constant. And the only way to get that constant is to by whatever that leading coefficient is times the numbers in the different factors that you get. So if we I'm not going to go into this in much detail because there is a separate video on this that you can look at. I definitely want you to watch that. But let's just go ahead and apply this rational root theorem in this situation. So it says our only possible zeros are factors, and I guess I could kind of explain. This leading coefficient is 4, so if we were to write this in fully factored form, we would end up with 4 factors. This would be x, 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 and x. We know that one of them is x plus 2, but we don't know what these other 3 numbers are. But we know that if we took 4 times 2 times this number times this number times this number, I'd have to get -6. So in other words, this number times this number times this number times this number has to be -6/4. So you can see why I'm going to look at factors of 6 divided by factors of 4 for possible numbers that could go in here. So using the rational root theorem, And it's called the rational root theorem or the rational zero theorem, because remember, roots are another name for zeros. So I'm going to look at factors of -6 divided by factors, oops, I'm not spelling that very well, by factors of 4. Now factors can be either positive or negative, so this could be positive or negative 1, 2, 3, or 6, or all numbers that are factors of -6. Positive, negative 1, 2, and 4 are all factors of 4. So combining these together to make all possible numbers, my possible rational zeros have to be contained in this list of numbers. So if I take all the numerators divided by 1, I would get positive and negative 1, 2, 3, or 6. Now if I take all the numerators divided by 2, I would get 1/2, 2/2, which is 1, 3/2, and 6/2, which are 3. So the only additional numbers would be 1/2 and 3/2. Then if I take all the numerators and divide them by 4, I could get 1/4, 2/4, which is 1/2, 3/4, and 6/4, which is 3/2. So the two additional ones are 1/4 and 3/4. I've already found one rational zero, and that's the -2. So I got that one already. Now, you can see that there aren't any numbers bigger than 2. So obviously those are not going to be in there. And 1 is positive or negative 1 clearly isn't a 0. So I'm looking at these fractions. So looking at the fractions, I'm seeing this 0 here and this one. So it looks like positive or negative 1/2 and negative 3/4 are both possibilities. So I'm going to start by looking at try negative 1/2, negative 3/4. Once I find one, then I can get down to a quadratic, so I don't really need to try both. So let's put in negative 1/2. Now you might think, oh, that's going to be horrible with synthetic division, but actually it's not, because my leading coefficient is 4, so I never really end up working with fractions at all. So 4 times negative 1/2 is -2, so then this is 4. And then 4 times negative 1/2 is -2, so this is negative 14. Negative 14 times negative 1/2 is a positive 7, so this is negative 12. Negative 1/2 times a negative 12 is a positive 6, so I get 0. So negative 1/2 is my other real 0. So what I have here now is f of x is equal to x plus 2. Oh, wait a minute. I need to divide again. Sorry. I know that one of my factors is x plus 2 and one of my factors is x plus 1/2. But this is still a third degree. I took my fourth degree and divided by my third degree. So what I have to do is actually divide it a second time. Now I just divided these both just to check that they were zeros. But what I'm going to do now is I'm going to take the answer to what I got when I divided. So this was an x to the 4th. Okay, so this is an x to the 4th. This is an x to the 3rd. So 4x to the 3rd plus 4x squared minus 14x minus 12. And I'm going to divide it again by my other known zero. So I'm going to put -2 here, and I'm going to just go through the division process a second time. Notice I cut off the remainder here. I'm not using that. So bring down the 4. This would be -8, -4, +8, -6, +12, 0. So now I've got it down to an x squared. So now I can write my polynomial in factored form, f of x. So I guess I had p of x, so let me write it as p of x. I've been doing f of x. Probably should have changed that on this one over here too. I guess I will for the printed notes. P of x. Okay, so p of x is equal to, I have my first two factors, x plus 1/2, x plus 2, and then my third factor is 4x squared minus 4x minus 6. Now my leading coefficient here is actually, I can actually bring a 2 out. I can actually divide all of these by 2. So this is the same thing as saying 2 times 2x squared minus 2x minus 3. So I'm going to bring the 2 out front. So I'm going to say p of x is 2 equals 2 times x plus 1/2 times x plus 2 times 2x squared minus 2x minus 3. Now why did I do that? To make the quadratic formula easier. The smaller the numbers I have, the easier it is to simplify it. This 2 does not count as a factor, remember. This is just a coefficient, my leading coefficient. My factors are only associated with possible values for x. So I'm going to need to use the quadratic formula. So I have setting 2x squared minus 2x minus 3 equal to 0. Using the quadratic formula, I would have x equals positive 2, because that's negative 2 here, positive 2 plus or minus the square root of negative 2 squared, which is positive 4, minus 4 times a times c, so times 2 times negative 3, all over 2 times 2. So that's my a there. Okay, so simplifying, that would be 2 plus or minus the square root of 4 minus a negative, and this is 24. 4 times 2 is 6, times negative 3 is, 4 times 2 is 8, times negative 3 is negative 24. 4 minus a negative 24, 28, all over 4. Now be careful simplifying this. Students do all kinds of crazy things, shortcuts. They want to cross out the 4 and make this a 7. They want to cross this out and say it's 1/2 plus the square root of 28, all kinds of crazy things. The first thing I want to do is simplify this radical. And this radical is the square root of 4 times the square root of 7, so it's 2 times the square root of 7. So I'm going to simplify the radical. So I have 2 plus or minus 2 the square root of 7 over 4. Now notice this is not an imaginary number, and I have 4 real zeros. I shouldn't expect any imaginary numbers in here. Once again, do not just say, oh, 2 over 4 is 1/2 plus 2 the square root of 7. You have to simplify these each separately. 2 over 4 plus or minus 2 the square root of 7 over 4. Then I can reduce 2 over 4 to 1 over 2. So I can say 1/2 plus or minus the square root of 7 over 2. Now, you may be running out of room and may have had to write over here, but I'm just going to write my list of zeros. So this is for example 4 continued. Okay, so I'm going over here with this. My zeros, my zeros here are positive 1/2, negative 1/2, negative 2, which you can see on the graph, 1/2 plus the square root of 7 over 2, and 1/2 minus the square root of 7 over 2. Now if you get a decimal approximation for these two numbers on the calculator, you'll find out that 1/2 plus the square root of 7 over 2 is 1.82, and 1/2 minus the square root of 7 over 2 is minus negative 0.82. So looking at the graph, let's check those out. This looks very reasonable for negative 0.82. This is my 1/2 here, and this looks very reasonable for positive 1.82. So those are the zeros for number 4.